This is why I want to show you an intuitive picture of why light fundamentally arises through the change of velocity of a charge just by simple geometric arguments. It shows that the radiation of light is a necessity, even without Maxwell. So let's take a look at a charge Q at rest in space. Since we are not allowed to use Maxwell, what are the things we can take into account instead? And the first one is of course Coulomb's law. To understand this force, we place a second charge, small q, into our space and see how it acts on it. The arrow on the second charge shows the direction and strength. The closer the two charges are, the stronger the force, and vice versa, because it scales as 1 over r squared. The direction acts along the straight line that connects the centers of the two charges. Let's now add many more test charges small q in a grid, which don't act on each other. This gives us a better picture on how the charge large Q is acting on its surrounding. Removing the test charges leaves us with an illustration of the electric field. Connecting the arrows into lines where the direction of force doesn't change gives us the electric field lines. Notice that Coulomb only gives us radial field lines, pointing away from the charge. This is our first rule. Now we are interested what happens to the electric field if we put the charge into motion. First, the easy case, where we only have constant velocity, and the result is not very surprising. The field lines still look perfectly straight and point radially away from the charge. The argument for this uses the principle of relativity, which in short just states that the laws in one frame of reference are the same as in another. That means as long as the velocity is constant, the electric field lines do not change and move along the charge remembering its velocity. This basically gives us parallel field lines for different constant velocities. This is our second rule. If we want to bring the system out of balance, let's say through a velocity change, we need to define how fast the velocity change is allowed to spread. And for that, we define our third and final rule, which is that the speed limit of information is a constant c given by special relativity, which is known as the speed of light. For our animation, that just means that the field lines move with the constant velocity c, giving us a natural lag time of information of the disturbance. Accelerating the charge gives then this wiggly motion of the field. The curves of the field lines show when we change the velocity. And not only that, it also tells us how the velocity is changed. And this is still not everything we get out of here. Our field lines are always going out radially and are perfect lines pointing at the position of the charge. So for curves to exist here, we need to have field lines which are perpendicular to the radial field lines. But where are these coming from when we only ever defined radial field lines in Rule 1? To actually understand this effect, we do a controlled experiment. Take a look at one explicit acceleration phase. We start with the charge at rest, accelerate it for time delta t, where the field radiated during the acceleration time is highlighted in orange, and proceed with constant velocity again. Now we can identify 3 regions. Region 1 shows the field lines for constant velocity, where the disturbance information did not reach yet, and therefore still point at the old position of the charge. The field lines of region 2 are dictated through the disturbance and therefore carry its information. And region 3 is after the disturbance again, with constant velocity, with the field pointing at its new position and moving along the charge. Additionally, we see that we carry 0 information about the velocity change parallel to the charge's motion and maximal information perpendicular to the motion. What is cool is that when we compare region 1 and 3, we see our rule 2 in action. The field lines are always parallel. But what is critical here, and what we want to understand, is that region 2 is not parallel to region 1 or 3, and therefore must contain perpendicular field lines. We will call the field lines perpendicular to the radial field lines transverse field lines from here on. And we want to understand where this transverse component is coming from, since our system never defined any other electric field lines other than radial. To understand that, let's take a look again at the acceleration phase alone and slow. What we see is that the field lines, even in the acceleration phase, always leave the charge pointing radially out of the charge at the moment of release. But since the field lines move with constant velocity only, but the particle is changing its velocity at every instant, the field lines inherit a different speed in the direction of the particle's motion. After some time, we see that this difference in speed brings the field lines farther and farther apart, introducing a transverse component. This means the transverse component gets bigger over time, while the radial component stays similar. But this is an important distinction. Even though this transverse component is introduced kind of magically to the system, in hindsight, it never was anything different than radial field lines. And that is the reason why that shift of positions is only characterized by the velocity change times elapsed time, making the curve wider for higher acceleration and narrower for lower acceleration, while the thickness of region 2 is only characterized by the time span of acceleration times c, making the region thicker for longer acceleration times and thinner for shorter acceleration times. Now that we understand how the transverse component of the electric field arises during disturbance, we want to quantify it to understand what that really is. We actually already got all information we need to do that, but to make the calculations as simple as possible, we will look at a very small time span of acceleration. Now we see that the velocity change is seemingly linear. Therefore, we can split the line into its components, forming a triangle, with the sides being the radial electric field, ER, and the transverse electric field, ET. That same triangle we can also characterize with the definition of positions, which we gave before. The position shift on this side is the velocity change times time, and the thickness of the region 2 is the field's velocity c times time span of acceleration. Since ratios of a triangle are constant, we can write this in this form, or even better, as an equation for ET. Now this is only for the field lines perpendicular to the motion, which is why we should rather write v perpendicular. And this we can also write as v sine theta, with theta being the angle between field line and direction of motion. Sine theta inherits the attribute that field lines more parallel to the direction of motion have a weaker transverse electric component. Therefore, we get this. And since we have delta v divided by delta t, we can also just write it as acceleration a. Lastly, we can write the electric radial field from rule 1 and the time t it takes for the field to reach some distance r away from the charge. With that, we get the final expression for the transverse field ET. So far so good. Now we have some things to point out. First, we want to know what the transverse electric field looks like. This is how it looks like with the same controlled velocity change as before. This is not very surprising. But what happens if we shake the charge repeatedly and plot the transverse electric field? And this is really cool. We get a wave in almost every direction in a donut-like shape. We can even see the wave in the equation of the transverse electric field ET. For that, we displace the charge by x, which gives us this acceleration. Putting it in the electric field gives us an equation describing a wave. And we can of course play around with it a bit. Increasing the acceleration, we get higher peaks. Changing the acceleration time, we broaden the peaks, and so on. We see the characteristics of the transverse field here now in action, which we observed before. But what we did not see coming from before is that the transverse electric field is proportional to 1 over r, instead of the radial electric field, which is proportional to 1 over r squared. This does not seem firstly like a big distinction, but it actually is. And it's not primarily about that 1 over r doesn't decay as fast as 1 over r squared. Let me give you a perspective which may change your understanding of power laws. A very simple question. When a field spreads out in 3 dimensions, why does it get weaker? This is a trick question, of course, because the answer is really, it doesn't get weaker. It is just being spread. You can see that very clearly when you look at 2 spheres, one inside the other. Every field line which gets through sphere 1 also goes through sphere 2. So we aren't losing on intensity or information over distance. It is rather that the field lines are being spread farther apart on the surface, which then is perceived as weaker field. And the surface area of the sphere goes as 4 pi r squared. So in a sense, space is following a 1 over r squared power law, which is why a field propagation is always fighting that. To get the power law of our electric field, we need to calculate the energy density, UE, which states how much electrical energy is stored in space. So the energy density of the radial field goes as 1 over r to the power of 4, which loses the fight against the spread of space, means it loses energy over distance till none of that is transported anymore over long distances, which is why we call the Coulomb field short-ranged. But interestingly enough, the transverse field with its energy density going as 1 over r squared doesn't die out. It cancels exactly against the spread of space, giving a constant, and this means the energy doesn't get smaller over distances, which is why we call it long-ranged. What this means essentially is that the transverse field goes through space without losing on energy, no matter how large the sphere is, and that means you can measure it at every distance. Bringing it together, the transverse field we have found through disturbance of the electric field has following properties. As all other field lines, it travels with the speed of light, c. It is transverse to the Coulomb radial field lines, it has wave properties, and most importantly, it doesn't lose energy over distance. By conclusion, this must be light. And we proved that with only 3 rules, without ever talking about Maxwell. Except that is actually still not the whole story. We missed one core part which we can't get out of this argument, and it is of course the magnetic component of light. Without Maxwell, we have no easy argument of why electric and magnetic fields are coupled. But in trying, we find a very interesting intuition behind it. And this is such a cool topic which deserves its own video. This is the reason I will leave that out for now and will follow up with part 2 to this topic. Now, before we close the video, I want to do a little detour. Everything we did before, we assumed non-relativistic particles. That means the charges were a lot slower than the speed of light c. Therefore, it is a natural question what happens when we go relativistic. One thing first, the main argument doesn't change. Only the spacing does. The main effect which comes from special relativity is the length contraction. So let's look at it in action. We keep the charge in the center. What we see is, in the direction of motion, the field lines get squished together. Therefore, the electric field is getting spread differently, namely stronger perpendicular to the motion and weaker in front and behind. Another effect is that since the charge is now of comparable speed to the field, it chases the field in front of it. When we bring disturbance into the system and change the velocity relativistically, the transverse electric field radiated here has also a different shape. It is still a donut-like shape, but it is no longer symmetric and is highly concentrated near the axis in direction of motion. Now, after all that, what can we say? I promised you intuition at the very beginning, and I think we got a lot of it. We started with 3 rules. Field lines go out radially, constant velocity just moves them along, and nothing travels faster than c. Out of that alone, we got a transverse field which propagates with c, which doesn't lose energy over distance, and which has wave properties. And that must be light. And the best part of it, I think, is that we could see all of that very clearly visually. There never happened a trick, because the usual way to tell this argument assumes the field lines have to connect, and the transverse component falls out of that. Here it never had to. It was always just radial field lines, whose starting points moved apart, which I find very satisfying. We got a complete argument out of very simple rules, and this is really astonishing without ever assuming Maxwell once how far we have come. Of course, with that we don't get the whole picture. The magnetic field is one of the missing pieces, and I will be happy to tackle this problem in the next video. If you have any questions left, let me know in the comments, and I will answer you the best I can. Other than that, thank you for watching.